Okay, today we would like to derive the Feynman propagator that we have obtained in previous class. The Feynman propagator is the solution to this non-homogeneous equation for free scalar particle equation of motion, where the current is just four-dimensional delta function. This 4 represents this delta function over x0, x1, x2, and x3. Okay? Before we go ahead, we just quote the final result. Delta function is, we already know that the four-dimensional delta function is a product of 4 delta functions. Each of them is the p0 exponential minus I p0 x0, that is delta x0, and delta x1, 2, 3 is the pi over 2 pi exponential minus I pi xi, something like that. The solution to this equation is actually simple. That is exactly the same as the delta function expression, except that in the denominator we have p squared minus m squared plus I epsilon. This plus I epsilon is very, very important, where epsilon is a positive definite and it is going to 0. So we have omitted epsilon goes to 0 plus. Okay? But it is convention to omit this limit. Let us just substitute this result into this partial differential equation, whether it satisfies the equation or not. Substitute this one to this equation, then we find this four-dimensional momentum integral is independent of derivative with respect to x, and that derivative acts on this exponential function only, and this is also constant with respect to the position. So if I pull this operator inside, what I get is for each derivative round mu e to the minus I p dot x is minus I round p mu e to the minus I p dot x. So if I take the derivative twice, I have minus p squared exponential factor. Right? So mass is the same, but I have minus p squared in it. Once the same factor appears in the numerator, the I epsilon doesn't matter, because I epsilon is important only if this term is vanishing. When p squared hits the m squared, then denominator vanishes, so I epsilon becomes important. That choose the correct amount of imaginary part of this integral. However, if this factor is appearing in the numerator, the denominator never becomes 0, so we just simply cancel these two factors even though there is no I epsilon. Okay? So over factor is just a negative sign. So this guy disappears and we put negative sign. Then remaining piece is just delta function. Right? So minus delta function, four-dimensional delta function. So this one satisfies the equation. Okay? But you'd like to interpret this result by integrating over the P0 energy integral. Then we will notice what happens. First of all, we can rewrite in the denominator. This denominator is p squared, and p squared is the p0 squared subtracted by momentum squared. Okay? And I have mass squared subtracted. So we have defined energy of the particle that is a positive important, positive definite energy. The particle is chosen to be E of P. Then this guy is a P0 squared subtracted by E squared plus I epsilon. If I want to integrate over P0, I have to find the residue. And if I want to find the residue, I have to factorize in the denominator. And simple way to find the pole is just collect these two things together, then it becomes a minus, right? Minus and the minus I epsilon. Note that if I square this, I have minus I epsilon squared, that is minus epsilon squared. Don't worry about that. Epsilon is a very small number. We just neglect epsilon squared. That is nothing. Just we just make, if you encounter expansion with respect to this epsilon, just ignore higher order. That's a simple way. So if I collect this together, then I can factorize using factorization formula. A squared minus b squared equals a plus b and a minus b, right? Using this factorization formula, I pull this one plus ep minus I epsilon and p0 minus ep plus I epsilon, right? So there are two poles. One pole is at minus E plus I epsilon. The other pole is at EP minus I epsilon. So this is P0, real axis of the complex number P0. Below this axis, I have positive energy pole, and above the axis, I have negative energy pole. There are two poles. The important thing here we have is everything is a real integral. There is no complex integral. So we would like to make use of the contour integral method. However, this integral itself is along the real line, real axis. And there is no pole at all on the real line because of this I epsilon prescription. Okay, so, however, we know that residue theorem is very useful for the contour integral. So, in case some integral, for example, if I do this integral, the answer is just depending on the residue of the negative energy pole. If I close the contour on the lower half plane, then I can collect the positive energy pole. Okay? The problem is that what we have to do is just this line integral only. I'm not supposed to evaluate this whole amount of integral. If I want to do this, I have to subtract the boundary part. Okay? Because this integral is from minus infinity to plus infinity along the real axis only. So, before we go ahead, we just want to find the contour integral first. If I close the contour on the upper half plane, the three-dimensional object is still there, but I have residue on the negative energy pole. If I substitute, that is, remove this guy and substitute remaining function by minus EP plus I epsilon. If I substitute in here minus EP plus I epsilon, I have minus 2 EP. And as you know, mass is non-zero, and this whole amount is a positive definite. So as soon as I substitute energy here minus E, then this becomes a minus 2E, and it is impossible to have this value vanishing. So I don't need I epsilon anymore. So residue for this guy is a minus 2 EP, right? And if I substitute minus EP plus I epsilon in here, what I get is a minus EP plus I epsilon, right? So, and I have 2 pi in the denominator, and I have closed the contour along the counterclockwise way. So I have 2 pi I, and 2 pi cancels, and the remaining piece is I. But I have minus negative sign in the denominator, so I pull this minus out, and minus I, 3-dimensional integral multiplied by 2 times energy of the particle. We are familiar with this vector. It is a phase space vector for a single particle. And remaining pieces, I have the same spatial oscillation part, I p dot x. But this energy part has been flipped because I have chosen negative energy pole. So it used to be minus I p0 x0, but that has been flipped into positive sign. So both of them are positive. But I cannot change the E of P because I have chosen the E is a positive. However, this integral is integrate over minus infinity to plus infinity, right? Minus infinity to plus infinity f of p dp. I can change the variable by p to minus p. Then what's happening is just is equal to right? It's because it is plus infinity to minus infinity f of minus p d of minus p, and this minus sign flip the upper limit and lower limit to become the same form. So I'm allowed to replace 3-dimensional spatial integral for the momentum. So this p can be replaced with minus p, and the measure dqp is still the same. So what I have now is I e of p x0 minus p vector dot x. That is, okay, I p dot x. Now energy has been changed. It is a positive. Okay. So because this momentum integral is from minus infinity to plus infinity, even though I have flipped the sign, so momentum direction has been redefined. That is hidden. So next, what about the integral, contour integral along the lower half plane? Everything is the same except that residue is now positive 2e, right? Because I am collecting this pole. What I substitute is e minus I epsilon in here. I have 2e in the denominator. And here, different from the above case, I have positive pole. And one difference is we are closing the contour along the clockwise way. So I have negative sign in front of it. So as a result, minus I vectors are the same for the two cases. And spatial integral is the same. And momentum integral, this part, the time oscillation part, have the correct sign. Okay? The difference between this and this is here we have freedom for the P0. P0 has been interpreted to be the contour integral. But here P0 is already substituted as energy shell, the on-shell particles energy. Okay? And then it's oscillating vector have the correct form for the positive energy particle. The whole difference, the general difference between the two is everything is the same except that it is flowing forward and it is flowing backward. So this is advanced and then retarded. Okay. But next step, we will check that this integral is the same as original integral if x0 is negative. We'll see that this integral is exactly the same as the original integral only if x0 is a positive. That means if x0 is a positive, the integral along this boundary vanishes. If x0 is negative, integral along this curve is vanishing. We can make use of Schwarz inequality, that is just absolute value of an integral is less than the integral of the absolute value of the function. That can be generalized to the complex variable, and I assume that you have already learned in the mathematical physics or complex variable in undergraduate classes. So what I would like to do is, if x0 is a negative, this integral is vanishing. This integral, absolute value of this integral along this curve upper half plane should be less than the integral of the absolute value. When the radius of this circle is very large, the P0 value, P0 is now complex. It is not real anymore. I'm considering this curve. P0 can be expressed as r cosine theta plus r sine theta, where theta runs from 0 to pi, right? Then dp0 is what? dp0 is dr e to the I theta. So there's r I d theta e to the I theta. If I take the absolute value, it becomes just r d theta. So I can pull this r out, and it becomes integral over theta from 0 to pi, and 2 pi is here. But when the circle is very large enough, you know, the epsilon EP is a constant. That is a finite value. But if the radius is very large, then this one can be approximated to be r squared. Something like that. Okay? So that r, this r in the numerator and r squared in the denominator cancel one factor, cancel at the 1 over 2 pi r and integration over theta. And if I substitute this P0 in here, the functional dependence on the angle theta looks like that. If x0 is a positive, then this integral can be the finite, or it can go infinity. Okay? However, if x0 is negative, as we learned in mathematical physics class, this integral vanishes after multiplying 1 over r. Okay? We can replace, you are supposed to make use of the fact sine function and this here pi, half of pi, theta, what's that? This is sine theta. This is theta over 2 theta over pi, something like that. So if you make use of this graphical information, you are able to find that this integral is a finite, and the finite piece is divided by 1 over r, multiplied by 1 over r, and it strictly vanishes as r goes to infinity. In the similar way, we can consider the integral on the lower half plane. In this case, the difference is minus I, and theta is again positive definite from 0 to pi, and we have negative sign in front of it. So this integral vanishes only if x0 is a positive. So if x0 is a positive, then this integral is vanishing. Then if x0 is a positive, this contour integral that we have already evaluated is the same as the original integral. If x0 is negative, the integral along the upper half plane, this guy is vanishing, and the original real line integral is the same as this integral that has been evaluated already. So there are two ifs. If x is positive, then the result is that. If x is negative, then the result is that. So if I combine the two results, then if x0 is a positive, then close the contour on the lower half plane. If the x value is negative, then close the contour on the upper half plane. And if I copy the result already obtained over there, I have minus I and one-dimensional phase space integral for the momentum, and inside the argument I have theta function for x0 with correct oscillating factor e to the minus ipx, and if x0 is negative, I have opposite directions oscillating factor. So this is a forward and this is a backward. Positive energy particle moves forward, the negative energy particle moves backward. Retarded and advanced. That's the meaning of what? That's the meaning of Feynman propagator. That's it.